Hi, hope you're doing well. Um, Today we are going to learn how you can simulate metamaterial or for some kind of metalens or metamaterial based absorber or metamaterial based solar cell or any other thing. You have to know how metamaterial actually work here, right? So we'll try to calculate transmission, reflection, and absorption of metamaterial. So let's get started. Okay. So at first we have to select model wizard, or you can select blank model if you wish. So at first, what we can do, maybe we can select 3D for now. Okay. So then we want to know about when to simulate actually optical behavior of metamaterial. So from wave optics, you have to select electromagnetic wave frequency domain. Double click here or add direct. Okay. So then what you have to do, you have to select study. So from study, we can, for now, maybe I can select um, web domain. Okay, maybe, yeah, maybe. Okay. For now, we can select frequency domain, maybe. Okay. So double click here, actually. Okay. So it will take a bit time. Okay. Here we go. So now, what you have to do? So at first, we'll do just some kind of basic structure of metamaterial. So as you know, metamaterial actually some part like mm, we can just place um, we can just place dielectric material on the top of metal actually. It makes actually metamaterial. So what we can do from geometry. For now, we don't need to select any parameters. Okay. Okay. Now what we can do just from geometry, we can select a block. So okay. So another thing from geometry for length, we may select nanometer as our length units. So from block, what we can do, we can uh, select the width of the block, maybe 100 nanometer. Okay, it's nanometer, right? So we don't need to put we can put nanometer here as a unit, but for now we don't need to put a nanometer because we already select the unit as nanometer. Okay, so and for depth, maybe it could be that will be 800 nanometer. Okay, and for height, maybe we can take it as okay, uh, 20 nanometer. Okay, for now. So build selected. So there we go. This is surface. Okay. So on the top of this material, what we can do, we can just place a cylinder, or we can place a block. So right now what we can do, just we can simulate this block. Okay, then we will introduce some cylinder or some rectangle. Then we'll understand how it's working actually. Okay. So to simulate this, what you have to do, we have to select another block. So we have to play, basically we have to pass through some light from on the top of this block actually. Okay. Okay, what we can do actually, delete. this block actually. We can duplicate this block actually. Right click, then duplicate. Okay. So maybe we can rename this as okay, no problem. We don't need to rename actually. We actually changed the material, so right now we don't need to select the material name. Maybe we can select it as air. Okay, we'll select it as air. Okay, so for this, air layer will start uh, from 20 nanometer, and it will comes from maybe 100 nanometer. Okay, there we go. So to see inside of this material, what you can do, you can just select this transparency, so it will be transparent, so you can see inside of this material actually. Okay, it's a cool feature of COMSOL actually. Okay, so it's air, and this one is maybe plasmonic material or any kind of material. Okay, so what we are going to do, we are going to, okay, another thing we have to do, we have to select a perfectly matched layer, because we, if some light gets stuck, scatter outside of this boundary, that could that should absorb actually. Okay, for that, what we can do, we can duplicate this model, sorry, this block, and we can rename it as PML. Okay, so it will start from 0 and it will go through 110 nanometer maybe. Oh, sorry, 130 nanometer. That's why. Okay, and then its width should be 20, and width should be 20. Okay. Oh, let's see. Okay, I will fix it. No problem. Don't worry. Okay, and height should be 140. Okay. So what we have to do, it will start from -10. Okay. So let me explain. Okay. The height of air is actually uh let me see. The height of air is 100 nanometer, and the height of this block is 20 nanometers. So total height is 120, right? So I select the height of PML is 140, so that we can add uh, absorber layer on the top 10 nanometer, and on the bottom 10 nanometer. Okay. So what we have to do, and for this side and this side, we have to actually uh, select -10, and okay, then so okay, yeah, it's okay. And for y-axis -10. Okay, so just perfectly working, right? So here you can see that you can't select the inner material right now. So what you can do, you can just okay, you can just select this view unhidden. So from view unhidden, what you can see, view unhidden. Okay, so click here. I'm sorry, view hidden. Okay, view unhidden only. Okay, so click here. Okay, click here. I'm sorry, view unhidden. Okay, then select boundary. Okay, so then select this one. I don't understand what's going on here. Why this one is selected? Okay, I don't know. It's, it's not working actually. It must work. Okay, let me check it. I don't know. My God, oh, I'm sorry. It's not the option. This one is the option. Okay. Um, so I'm sorry. So we have to view unhidden. So we have to select view unhidden. Then you have to select this one. Okay. Click and hide. Okay. Click here. Then cursor will look like this. So what we have to do, you have to just right click of your mouse. Then you'll see. Okay. Select boundary. Okay, it's okay. So then select boundary, then you have to click here. Then you can see that you can, or you can also hide this layer as well. Then just click here, then it will work normally. Okay. So what I did actually, we hide this layer and this layer from the geometry. That's why we can select inner object easily actually. Okay. So now from material, I have to select add material from library, or you can select blank material for now. So from blank material, we don't need to actually. What's going on? Okay, okay, no problem. We need to select this one, and we need to deselect the bottom layer. Okay, so okay, we select this one and this one. Okay, so it's the air actually. Okay. Then what we have to do, we have to add material from library. So we have to add actually, maybe we can add gold or silver. Right now I'm going to add silver, experimental. Okay, thin film, experimental thin film, the silver. This one is working from 0.191 micrometer to 20.9 micrometer wavelength. So I'm sorry. I'm going to select this silver. Okay, I'm sorry, but let me see. Silver or silicon dioxide. Okay, okay. So silver will be the on. I'm sorry. Okay. So there is another way to select this domain actually. So you can select from this here. So select box, click here, and then select this way. Okay. So that's the thing. Okay, this is actually silver and this one actually air. So now what you can do, just you can okay. Oh, sorry, we didn't select the refractive index of air. So refractive index of air is 1 actually. So that's all. So we select all the materials. Okay, now what we have to do, we have to select the PML. So from definition, right click, perfect image layer. So it's kind of Cartesian. Um, spherical or cylindrical, which may be, I'm sorry, user defined. We may select user defined. Number of direction, 3 direction, thickness of x direction. Okay, PML actually. Thickness of x direction is 120, and height 140. Okay, so thickness of x direction is 120, 20 nanometer actually, nanometer. Y direction 120 nanometer, and Z direction is 140 nanometer. Okay, this is the PML actually. Okay, and what we can do, and another advanced thing you can do here, from view, you can hide the PML actually, hide from physics. So you can hide this domain from physics. So it will not hamper your simulation actually. Okay, so you can see that PML is kind of hide here, right? So you can do anything easily right now. Okay, so you can see that one is PML. So the PML is hide from this domain. Okay, let me check it. Okay, and 2 and 3 is working perfectly. So from electromagnetic wave, what we have to do, we want to simulate, we want to select a port, and we'll pass through light, and we'll see how it's actually working. Okay, so from simulation we have to select, let me check. Okay, another thing what you can do, you can do group by space dimension. So it will group by boundary and domain. From domain, I don't need to do anything. From boundary, we have to do something. Okay, so that's how, we just reduce our options. Okay, so you can find out your options easily from this kind of this option, right? So we want to select port. So you can select port, and this port we want to work on. So from this port we want to just uh, we want to just introduce some electromagnetic wave actually from this port. So for port name is 1, and port is 1 actually, and port input power we have to select some input power. So we maybe select okay, 1 watt as input power, and the wave will pass through the electric field. Okay, this is the propagation constant, so we don't need to do anything here. Okay, okay, uh, okay. Electric field. Okay, so another thing you can do, you can select the port type. So there is different type of port, like numerical port. So from numerical port, you have to just select the input power, nothing you have to select actually. From rectangular port, so from rectangular port um, uh, we just pass through light um, from rectangle, right? So it's our rectangle shape, so we can pass through rectangle, we can select rectangle port actually. And there is another way, coaxial port still work when you are working on hollow core fiber, right? Okay, circular port when you are working on circular type of shape. Okay, so periodic port, this kind of port actually we use most, uh, periodic ports actually. So right now, so from periodic port you can change the angle of incident or azimuth angle. Okay, azimuth angle of incident. So that's the cool thing of periodic port actually. So right now we can work on periodic port. Okay. Okay. So and another we need another port actually. So we can duplicate this port. Duplicate, and we need to off this port because we want to get we need to collect output from this port. So deselect the first port and select the bottom one. Okay, so this is our input and this is our output port. So yeah, then from mesh what we can do, okay, another thing we can do, we can select periodic condition. Okay, so oh, sorry, we don't need to do periodic condition right now because we select perfect image layer. That's why we don't need periodic condition. Okay, so from mesh, what you have to do, you can select physics control mesh, but it sometimes may take some time. So what we can do, we can select size. So we are using user control mesh. Okay, from size, you can disable this size. We can work only this on this size, and then what we can do, we can select boundary layers or identical mesh. Okay, what we need to do, identical mesh. So this and this one. So this is actually x directional part, and this one is the another part of x direction. So these two parts should be identical. Okay, and duplicate the, okay, no need to duplicate. So then we need another identical mesh, and this identical mesh actually will make identical mesh for both side of y-axis. Okay, so here this one and this one. Okay, then what you can do, you can select free coordinates or mapped mesh, but sometimes it may hamper your model actually. So right now we are selecting free triangular. Okay, maybe we can select mapped mesh. Something cool, make your model cool. Okay, entire geometry. So build. Okay, it's the model is done. Okay, now what we can do, we can study. We can select a study frequency domain. So from frequency domain study, what we can do, we have to select a wavelength. So the wavelength is, let's say, L is the wavelength. This is L, and we are we maybe want to work on 60 nanometer wavelength. Okay, so this is our wavelength L. So from frequency domain, we need to select the wavelength as L. Okay, this is the velocity of light and this is our wavelength. So velocity divided by wavelength is equal to frequency. Okay, so maybe we can simulate right now. Compute. So there we go. There is some problem here. Okay, so let's find out which kind of problem it is. Okay, that's a cool thing, I think. So I need periodic condition, right? Where is the periodic condition? Uh, perfectly condensed. Okay, so periodic conductor, periodic condition is not working because we select PML. Okay, so this one actually PML, so we cannot select periodic condition. But if we don't select periodic condition, then the port will not work. So let's change the type of port, rectangle. We can select port as rectangular port, okay, or rectangular, okay. Now we can simulate it. Maybe it will work, or maybe okay. Again, the problem condition should be appear. It's to be a boundary. Okay, select condition. Okay, there is some problem. So what you can do, we can use user interface. Oh, sorry, user defined port. Okay, it will work or not, I don't know. So that is the problem. Okay. Select condition should be appear only on an interior boundary. Okay. So for now, we may disable the perfectly matched layer and we may disable this perfectly matched layer for now actually. So this one is air and this one is silver. So for because we disable the perfectly matched layer, so from boundary we have to select periodic condition. Okay, so periodic condition. This one is for x direction. Okay, so this is the x direction. So we have to select periodic condition for x direction and we can, okay, continuity. Okay, okay, and there is another periodic condition. So we can rename it as y for y direction. Okay, so you have to select periodic condition for y direction. Okay, and from port. Okay, what you can do, you can select periodic port, periodic port. Okay, so then maybe it will work. So right now I'm simulating with you. I didn't simulate meta surface before in COMSOL, so it's my first time I'm simulating actually meta surface in COMSOL. So properly does not include all variable in XMesh. What? Okay. So map mesh is not working here. So disable this mesh and add free tetrahedral. Okay, then build this one. Okay, then we can run study again. So this is how you have to find out the problem of study, and then you have to solve the problem of study. Okay, so sometimes you may face some problem in COMSOL when you run the study, but you have to solve all the problem. Okay, so the study is done. Okay, it automatically provide our drive value, reflectance, transmission, and absorption. Okay, so but I want to see some electric field distribution. Okay, from 3D plot graph. Okay, what do we have to see? Volume or surface? You can select anything. Okay. Uh, okay, you can select volume. So it will directly provide you an expression of electric field norm. Okay. Okay. This is the electric field distribution actually. So what we are seeing here, you can see that the electric field is electric field intensity is very high on the top of this here and very low here. Electric field distribution is very low inside the silver. So what happened here actually? So we will see actually what happened here. So for that, what we can do, we can select 1D plot group. Okay, for 1D plot group, we can select global. Okay, and from global, what you can do, we can add some equation from ports. What we can do, we can take transmission. Okay, reflectance. uh, Okay, S parameter. Okay, so from S parameter. So S parameter does not provide you directly the transmission and reflection because it is S parameter is kind of complex thing. Okay, so if you want just the amplitude of or the real part of transmittance and reflectance, you have to select from here. Okay, total reflectance and transmittance. Okay, total transmittance. Okay, so you can see this is the total transmittance is 0, and then I need another one. So from port, I need total reflectance. Okay, so total reflectance, let's see. Here you go. Total reflectance is kind of 0.9541. So what happened here? Actually, light comes from this port and light get absorbed kind of 0 point something percent, and total light get reflected here again. Okay, so we can see this kind of thing if we just run time domain analysis. Okay, so I will just okay. And another thing I can do for you, actually, we can calculate the no, we can actually plot the absorption. Okay, so total absorption. Okay, I'm sorry, what I did, Control Z. Okay, so from Control Z you can get this thing again. Okay, yeah, we have to select from here. Okay, okay. Oh, sorry, total absorption. Okay, so here we go. Here you can see this is total transmittance, this is absorptance, and this is the reflection. So light absorbed inside gold is very less, but maximum light get reflected, and transmittance is 0 for silver. So what we can do for now, we can reduce the height of the silver, then maybe some light get transmitted. So height of so for now actually, maybe we can select the height of silver, maybe 5 nanometer. So here we'll start from 5 nanometer, right? Okay, so okay, so then we can simulate again. It will take 10 or 20 seconds. Okay, let's see what happened. Okay, it's open actually. Okay, it's done. So here you can see there is some sense. So now, wow, you can see total transmittance is 0, but absorption get increased and reflection get reduced, right? So 0.93 and 0.069. So thin layer silver is absorbing more light. Okay, that's our findings. Okay, so what I told you that we can see how light propagating through the silver and light get reflected. So in time domain we can see that. Okay, so what we can do, we can simulate time dependent. Okay, so we can simulate time dependent analysis. So what happened? Okay, so electromagnetic wave does not provide us time-dependent analysis, but we can do it another way. Okay. How we can do it? Okay, delete these studies, and then how we can also we want to do the time-dependent analysis, right? So how light is propagating through the um, observer. Okay, so to do that, what we can do actually what we can do, let me think what actually we can do. Okay, from study, so let's find out web domain, frequency domain, mode, frequency, eigenfrequency. Okay, it doesn't provide us any kind of time domain, find time domain analysis. So how could we do the time domain analysis? So I need to know actually how we could do the time domain analysis. Hmm, there should some way actually. Okay. Adaptive frequency. So it does not provide any time domain analysis, right? So for that, okay. So it doesn't provide any time domain analysis. So what we can do actually? So sorry. So now, what I told you, we are going to simulate meta surface, right? So then uh, I actually do the simulation of meta surface. So from geometry, what we can do, we can select cylinder and the radius of the cylinder. Uh, the weight is 100, so we can select the radius of the cylinder, maybe 90 nanometer. Let's see. Okay. It's okay. Radius, sorry. 90 divided by 2. So the position is kind of, so we need to place the cylinder here, right? In the middle of this rectangle. So height should be maybe 50 nanometer. Okay. So we should place the cylinder on the middle of this rectangle. So how we can place it? So the height is 100. So this should be 50 and y direction should be 50. That's how it will work. Okay. And the position should be 5 nanometer. Then it will be top on the, okay. And then height, maybe we can reduce the height. Maybe we can select 30 nanometer as the height of the cylinder. And then here, okay, there you go. So uh, we can just select material from material library. So we need to maybe we can select silica. Sorry, silicon dioxide as the material of the top of the cylinder. So scattering plus inorganic material. Sorry, organic material, right? Organic class organic material from organic material. Um, okay, let me oxygen dioxide. Okay, thin film. Okay, from here, yeah, we got it. Silicon dioxide. Okay, we may add this one. Okay, so how you can select this cylinder? I think you know. I already told you. So you have to select the select box and then select the total domain. So that's how you can select the cylinder, right? So from port on, light will come from port 2. Select the absorption, periodic condition. Okay, identical mesh. All the mesh is working well, I think. Okay. And I want to tell you, please memorize this absorption and transmission and reflection. Okay. Then we want to simulate this model again. Compute. Let's see what's happening here. Okay. Okay, it's done. Right. Okay, let's see. Okay, now we can see the absorption get increased and the reflection get decreased, right? Yeah, that's how it's actually work. So, but transmission is uh, zero as usual. Okay, so you can see that there is a very good resonance here. So we, so you will tell me that where is the resonance? So you can see the resonance, right? So the resonance is actually happen uh, actually okay, I can actually prove it. Okay, from data set you can select uh, mode 3D. Okay, array 3D. Okay, you can select array 3D. So the size of x-axis. So the resonance creating x-axis. The side of x-axis. Maybe we can select. Maybe we can select two for now. Okay, plot. I'm sorry. Okay. So no. So from 3D model, we can select array 3D. Okay. Okay. So here you go. Now I can prove it. I'm sorry. So actually, what I'm expecting that the resonance we will see the resonance between these two uh, silicon dioxide. Okay, but it does not showing like that. But we can prove it another way in another way. Okay, so let's see how we can prove it. Okay, so we may reduce the radius of the cylinder by 90 divided by 4. So then we can place it at 25 nanometer. Okay, then we can just duplicate this cylinder. We can place it at 75 nanometer. Okay, we are placing two cylinder on the top of this. Okay, so then it should be silicon again. Okay, from select box you can select this one. Okay, as well. Okay, this one is not air actually. You can remove this one, silver. Okay, port, everything is fine, I think. Build all. Okay, then simulate it again. But you can remember the absorption, the transmission. Okay, whatever. So plot. Oh, sorry, compute actually. Let's see what happened. Okay, so surely what happened? Okay, let's reduce the absorption, but it enhance the reflection, right? But there is no resonance here, right? Um, okay, it's okay actually. Okay, so maybe it's because of the wavelength. We're simulating at the wavelength of 600 nanometer, but you can see the refractive index of silicon dioxide is it's absorbed at the lower wavelength, right? And for silver, it absorb light at okay, it absorb light. Is it Ni? Okay, yes. So it absorb light actually. Let me see. Clear it. I'm sorry. You can see we are simulating on 600 nanometer. Okay. This value of K is at 600 nanometer. This value of K is kind of 3.663. So yeah, and okay, the real part of K of it is actually very high. That's why the light of uh, okay, in this wavelength actually the real part is very high. So no, it's not that much high actually. Right, it's not that much high, but light get reflected. That's the thing actually. But double silicon, sorry, cylinder is not working well. So what we can do, we can just uh, again okay, enhance the diameter, and it may be enhance the radius of this cylinder. Then maybe it may enhance its performance and the height of the cylinder. I don't know it will work or not, but maybe it will work. And what I want to do, I want to enhance the height of the block. And another thing I want to do, I want to place the cylinder okay, sorry, inside the and place the cylinder inside the silicon silver. Okay, then I don't know what will happen, but let's see what's happened. Okay, this is silicon dioxide, this is silver, and this is air. Okay, let's see. So we are simulating metamaterial. Okay, maybe we will do something interesting after this video. Uh, okay, let's see. Okay, I think something interesting happening here, right? Okay, let's see. Okay, absorption get enhanced, right? You can see the absorption is right now 0.1. Okay, and the reflection is reduced. Yeah, it's very good findings, right? So this is how you can make a perfectly absorber. Okay, so I don't know for this wavelength, but let's check another wavelength. Okay, so for maybe 300 nanometer. Okay, let's check for 300 nanometer. Now compute. So actually, we are running for 600 nanometer. So we don't know this 600 nanometer will is the perfect uh, wavelength for this kind of structure. So we are just exploring this kind of metamaterial, right? So that's the thing. But in maybe our next video, we may try to observe how actually we can introduce time domain analysis. Okay, so for 300 nanometer is, I don't know how it's okay. Okay, here you go. For 300 nanometer absorption is very high, comparatively 600 nanometer, right? And if transmission, what? Let's check. Transmission, this one is transmittance. Hey, look, reflectance is very low here. Reflectance is very low. Transmission is very high. Light get transmitted through the structure from this here. Okay. So this is the interesting thing. Okay. This is the interesting thing of metamaterial actually. Okay. I think you understand how it's actually working. Okay. I don't know if you understand or not, but I think you understand. Okay. If you understand, you can comment below, or mm, we will maybe work on time domain analysis for this kind of a structure later. Or you can actually ask which kind of metamaterial um, simulation you want, maybe solar cell, maybe lens, maybe absorber, anything you can ask. Okay, thank you everyone. Thank you for your attention. Goodbye.